All right, we'll get started. While the stragglers are joining, I'll run through my SEONC news and I'll leave the bulk of the time here for our real stars of the show. Thanks so much for joining. Today we're going to be hearing from Bridges to Prosperity, and specifically they're going to be talking a little bit about the design and construction of a pedestrian cable bridge in East Africa. I am super excited to have them here today. I know for me, this organization really connects the dots and reminds me of everything I love about structural engineering. So hopefully you guys will get some of that same excitement in the session here today. I'm Emily Guglielmo. I'm currently your SEONC president. I want to just highlight that today is a big success for us on a couple of our strategic initiatives for the year. First one being, we made it a goal to do a better job reaching out to some of our partner organizations, specifically the SEIs and ASCEs. And I would like to welcome our SEI and ASCE members who are joining us here today. We're really excited to have a broad base of attendees from all three organizations. Second, we made it a goal to reach out to our students a little bit more, especially in this remote COVID world. And we're very excited to welcome a bunch of students to the session here today. Lastly, we recognize that SEONC traditionally has been a very heavily focused on the building community, and we made it a goal to provide some content to our non-building or less traditional markets in SEONC, and so we're very excited to be highlighting a bridge topic here today. With that being said, I would like to just very briefly thank our annual sponsors. Without this group of very philanthropic giving organizations, SEONC wouldn't be able to take on the initiatives that we have done this year. Similarly, our sponsor firms, this group here recommends is our very first ever firm sponsorship group. There are new opportunities for firm sponsors. Please email the office if you're interested in potentially a firm sponsorship. And this year we actually gave a new sponsor benefit to these firms, which was a free booth at the inaugural SEONC Career Fair. Tomorrow, we have our very first SEONC Career Fair. We have over 50 SEONC firms, nearly 250 students from 20 plus universities joining us. So for the students listening here today, it's not too late. You can follow the link at the bottom of the page to sign up for the Career Fair. And for any of the firms, be it SEONC, SEI, or ASCE firms looking to hire, it's not too late to sign up and purchase a booth. So information here at the bottom of the screen. Before I hand off, I do just briefly want to remind our membership that we have just launched our DEI Restricted Fund Endowment. And through the end of March, we are grateful to be having a 3-to-1 match from a CSI up to $100,000. So we've been very impressed by our SEONC community's contributions in the last few weeks. We are building up a really nice base for our endowment, but we would love to see a contribution from all of our members and all of our member firms. I'd like to just very quickly remind you that SEONC is incredibly active right now. We have a handful of events coming up, both some that are free, such as our Engineering Interactions series, and our next one is on February 16th. It will be hosted by two of our most senior SEONC past presidents, F. Hirsch and Loring Wiley, telling stories about their careers. We will be doing an OSHPod updates to 2019 CBC later this month. We have a few SE3 events coming up, and then some HSS connections and detailing in March. And for all of the SEONC members, please remember to log in to the website. When you do that, you will have access to all of our committee meeting schedules and links. This is the best time to join a committee. You don't have to jump on BART. You don't have to go downtown. You don't have to take the elevator up to a big conference room. Just jump on a Zoom meeting. Listen into some of our committee meetings, see what they're up to. We have incredibly active committees right now doing really fabulous things for SEONC. With that being said, I would like to hand off to our SEONC Programs Chair, Badri Prasad, who is going to introduce our session here today.
Thank you, Emily. Again, this is Badri Prasad. I'm the Program Committee Chair, and welcome you all to this very exciting presentation today, Bridges to Prosperity, Design and Construction of Cable Bridges in East Africa. We got two speakers here who would be talking about this, and the first speaker would be Devin Connell. Devin Connell is a corporate, oversees the corporate partnership program at Bridges to Prosperity. He is pretty passionate about connecting engineering and the construction industry with the infrastructure work. Currently, he manages over 40 partnerships with EAC companies to support the B2, Bridges to Prosperity mission. And Kevin has a degree in civil engineering from Portland State University, and he lives in Denver, Colorado. And the second speaker would be Nico Turini. I hope I pronounced his last name correct. He has a civil engineering and a master's degree in structural engineering from Modena in Italy. And he has about 6 years plus experience as a design engineer. He joined this organization in 2017, and currently he lives in Kigali, Rwanda, and he would be the second speaker, and he would be talking about the Bridge to Prosperity and particularly the projects that he's working on. Welcome to Devin and Nico. Over to you guys.
Wonderful. Thank you so much, Badri, and thanks for having us here today. All right, I'll do the classic share my screen and make sure you can all see it before I get going. Let's see.
So Devin, one more thing I want to remind our audience that if you have any questions, please submit it in the chat, and the speakers will address it at the end. Thank you.
Wonderful. Thank you. All right, so can everyone see the full presentation here? Am I sharing correctly? All right, wonderful. I'll go ahead and get started. Awesome. Well, as Badri mentioned, we are going to be giving a presentation today on pedestrian cable bridge design. Right now, our focus is in East Africa, so we'll talk about that a little bit. I'm just going to give you really a pretty quick background on who we are as an organization, why we do what we do, so you have a little bit of that understanding. Not going to dive into too much detail. And then I'm going to hand it over to Nico, who's going to actually dive into the construction and design of the specific of our projects. So we're going to go ahead and get started. Real quick background on myself. As Badri mentioned, I graduated with a degree in civil engineering, worked as a structural engineer for a few years in Oregon before hopping on a plane and heading off to Panama, where I managed our operations there for a little while and actually picked up this street dog who is back in Colorado with me now. As you can see here, she doesn't actually love being picked up, but I do think she's pretty happy to be back here in Colorado. And since then, I've traveled around all of our programs in Latin America and East Africa, and now currently oversee all of our corporate partnerships. So again, that's a part of our program we're not going to dive into today, but I do want to let you know, and if we have time for questions, we can maybe bring it up, that we do partner with a lot of firms in the engineering and construction industry. And if you're interested in getting your company involved, we'll have our contact information at the end, and I encourage you to reach out. I actually saw one of your donors on your previous slide, Structural Technologies, is actually one of our most recent partners. We're really excited to have them on board as we move into 2021. Okay, so who are we? What do we do? Well, Bridges Prosperity envisions a world where poverty caused by rural isolation no longer exists. Our mission is to work with isolated communities, create access to essential healthcare, education, and economic opportunities by building footbridges over impassable rivers. Wonderful. There's our vision and mission. You've probably read them for so many organizations in the past, but what does that really mean? Why do we really do what we do? Well, I want to ask you for a second to really try and put yourself into the shoes of this man here in Bolivia. Now, it's pretty hard for us to do. A lot of us aren't actually commuting these days. Most of us are working from our home office. I know I am. But try and imagine it each day to get to work. You had to walk 30 minutes down the trail up to this cable, hook onto it with a pretty rudimentary hook, and zip line across this river, day in and day out as that river rises during the rainy season and falls during the dry season. That's the reality for so many communities in Bolivia, like this one that we went in and actually built a 130-meter suspended bridge for shortly after this photo was taken. Or maybe imagine that this is how you sent your kids to school every day, and you hoped that, during the rainy months that the river didn't rise too high to wash the bridge out while they were in school. And then they have to make the decision whether they swim across the river on the way back or they stay by themselves or with other students on the other side of the river until the river drops the next day. Again, most of us now are starting to have a hard time having our kids walk a couple blocks to school on their own, for better or worse, in the US. So, you could only imagine what it's like for these families as they send their kids across these types of structures day in or day out. Or how about this is how you got to the market every day? Now, for me, this photo really speaks to why we do what we do. If you look in closely here, this bridge is actually made out of barbed wire. The suspenders, if you can call them that, the main cables, if you can call them that, the ties on the decking, it's all made out of barbed wire. And this really speaks to the need communities see for these projects. So this is an example of a community in Nicaragua that wasn't able to get the support on their own from local NGOs and the local government, and so actually took it into their own hands to build this bridge. We then worked with this community to replace this with one of our structures years later. Or finally, take a look at this photo. Now, I don't know about you all, I've got a lot of good friends, but I don't think I'd be trusting them to hold each side of this rope as I climbed across. But unfortunately, this was the reality for this community in Ethiopia for decades. This community actually destroyed this structure on their own during a war to keep out the opposing forces from entering their community, and had to live with that for several decades until this photo was put in National Geographic and is actually the founding story for our organization. Our founder saw this photo, said, hey, I think there's something we can do about it, and went and put this bridge in their place. Now, there's a reason why we didn't just stop at that bridge. We went from there to grow into what we are today, almost 20 years later. And this is a big part of that reason. World Health Organization actually estimates that 1 out of every 7 people in the developing world lack safe transportation access to essential services. That's almost 1 billion people in the world can't get to where they need to go on a daily basis due to infrastructure. But why footbridges? Infrastructure is obviously a big thing. There's a lot of different factors at play there. Well, we focus on footbridges for a lot of reasons. A big one is 1 out of every 7, that roughly billion people around the world, the majority of them live in walking communities. So if you go to one of our communities in rural Rwanda or Uganda or Panama or Nicaragua or really anywhere around the world, you'll see that there aren't roads in these communities, there aren't cars, there are footpaths, there are motorcycles, and there are cattle of different sorts. Their reality is a walking reality. And so the investment you put in for vehicle infrastructure oftentimes isn't realized in a reasonable enough time span compared to the much lower investment you can put in for pedestrian infrastructure. A study that was actually done by the University of Notre Dame and Yale showed pretty remarkable results on our projects in Nicaragua. Really, one of the big ones here I want to point to is the 30% household income increase. It really blew us all out of the water. It was pretty a staggering impact that we didn't necessarily expect. And when we saw that, we said, we knew we were on the right direction before, but now we definitely do. What that number means is you can go in and build a bridge for $60,000 to $100,000 for a community, and they can see that local community and income increase can see a return on investment in a matter of years. Opposed to, decades when we're talking about larger infrastructure projects. So how far have we come on our mission to end poverty caused by rural isolation? Well, we've worked in 20 different countries around the world, built over 350 footbridges, and connected over 1 million people with those footbridges. We are obviously incredibly proud about that. We're very excited about that landmark. But we have a long ways to go. As I said earlier, close to 1 billion people around the world lack safe transportation access, and we've hit 1 million of them. We're only scratching the surface. And so where we're moving forward is figuring out a way to make a bigger impact. And our first kind of example of that is what we're doing today in Rwanda. We are actually partnering with the government of Rwanda to build up to 300 bridges over the next 5 years. We're actually in year 2, so now over the next 4 years, throughout rural Rwanda, connecting over 1 million people in the country alone. It's going to be an example of how you can partner with central governments and big aid and nonprofits to really meet the entire pedestrian infrastructure need of a country and hopefully change the economic landscape and livelihoods of those communities as they move forward, which we will then kind of take out into other countries in the region and then globally. So just to give you an idea, this is where we're working right now. We're also working in Uganda, but our big focus today is in Rwanda, and we're working in all of these different districts in the country, mainly in Western Rwanda, because that's the mountainous area. And as you can see here, the darker regions are where we're building more bridges. So in some districts, as you can see, up to 11, and a lot of districts, 1 or 2 or 3 bridges, depending on their need. Again, that was rapid fire, but I want to leave a lot of time for Nico to dive into design. So if you have any questions on, the general stuff, general background on our organization, why we do what we do, what we're doing in Rwanda, jot them down. And if we don't have time at the end, you'll have my contact information and we can connect afterwards. Always happy to talk more about it. So wonderful. Thank you. With that, Nico, I'm going to go ahead and hand it over to you, and you can take them into design.
Thank you, Devin. Ready to go here. And do not worry, as Devin was saying, you're going to have our contact information in the last slide, I promise. So just note down your questions if you want to write them in the chat to get the answers during this presentation. If not, you're not going to be able, you just email us. Can you all see all right? Devin, can you see all right?
Yeah, perfect.
Good, fantastic. So thank you again. I'm Nicola Turrini, and today I'm going to walk you through the main aspects of the design and construction of P2P suspension bridges, which is one of the 2 types of bridges that we do. But let's start with a short and personal introduction, as Devin did. As you may suspect from my name, I grew up in Italy, in a really beautiful town called Modena, where I completed my bachelor degree in civil engineering and my master's in structural engineering. And during my master's, I got the opportunity to get a European scholarship called Erasmus. And that gave me the chance to move to Madrid in Spain to work as an intern for an engineering firm. And that was the start of a long 3 years in which I had a lot of fun, but I also got a lot of experience in bridge design. And in 2016, then I took, at the time, it seemed like a crazy step of leaving my job in Spain and applying as a volunteer for Bridges to Prosperity, ending up being sent to Nicaragua, flying to the other side of the ocean for the first time, and having a lot of hands-on experience working on building cable bridges with my own hands for 9 life-changing months. And thanks to my engineering background, I then made it into B2P. And in 2018, I got the opportunity to move to Rwanda in order to help growing our local engineering capacity. And until at the end of last year, 2020, I've been working for the Rwanda program as engineering manager, focusing on surveying, design, and quality control for all the bridges built in Rwanda. I now jumped in a marketing role, bringing my technical experience with me, and that's why you see me here today in this webinar. But what do we actually build in Bridges to Prosperity? We build cable bridges, and they are structures characterized by light walkway systems that permits this kind of structure to span across wide valleys with no need for mid-span supports and assure moderate dimensions also of the substructure as well. We, as I was saying, we have 2 main standard bridge types. The first one is the suspended bridge, which is more of a hammock type, the kind of bridge that you find in movies like Indiana Jones. And referring to the representation that you can see in the slide, the abutments are made by a frontier system with a tower, a concrete tower on top, and an anchor in the back, all connected with lateral walls that create a ramp which is filled with rock and topped up with a concrete slab. Then the walkway is made by main steel cables and suspenders and the walkway system that we're going to see. The suspension bridge is the other type of bridge, which is more iconic, similar to the Golden Gate Bridge that all of you should know pretty well, as long as we are also in California right now, if I'm not wrong. So here the main cables hang from taller towers, and the walkway is actually upward in order to improve the clearance below the bridge for flatter river profiles, like the one that you normally find in floodplains. Concrete pedestals are below the towers and transmit the load to the footings below, and an anchor, a deadman anchor type is in the back, anchoring the main cables. This presentation is going to be especially about suspension bridges, so we're going to refer to this representation more than one time, so I'm not going to stop right now, but we're going to go back to that. We can start now with a brief overview of what it takes to pass from selecting a site to have a trail bridge built there, following our general steps. In particular, the Rwanda program as an example, where a comprehensive assessment of need for pedestrian footbridges was undertaken in 2018 across the entire country. Once the pre-assessment was carried out following the diagram in the slide, asking a small number of precise questions to pre-evaluate the need of a B2P bridge in each location, then a trained group of assessors was sent to site in order to carry out the full technical and social assessment. Each assessment then has been post-evaluated by the engineering department in which I was working in order to decide if each site was technically feasible or not for a B2P bridge, approving in this way around 300 sites out of almost 1,500 sites total. Once the list of approved sites was ready after the assessment, our research partners worked on a randomized order to be followed for the construction of our bridges in each district, basically a randomized controlled trial study. And these were like Notre Dame and Yale, and I think also University of Colorado. Correct me if I'm wrong, Devin. Each year, the same list is followed to decide which sites to survey in each district in order to design and build the bridge there. Once the site survey visit is scheduled, then our surveyor will get in touch to district and community representatives to plan the visit. Once on site, a bidimensional survey is carried out with a total station to define the profile of the riverbed along the line, which is selected by the surveyor, following criteria that we're going to see in the next slides. Then once we have the deliverable of the survey, the deliverables of the survey, which are topographic data, photos, videos, GPS coordinates, and geotech evaluation. All of this data is then used to design the bridge to be placed there or to reject the site. A set of technical drawings and a bill of quantities, as in every engineering work, will be then created based on the design. And once the drawings and the bill of quantities are ready and approved by the district, a bridge can be constructed with our construction team and finally inaugurated and open to the public. Before diving into too much detail about main design parameters, let's start with some basic definitions that may not be completely familiar if you're not specifically working with cable bridge design. So once the site is selected, the river flow direction will be defining the names of the different areas around the bridge, starting from the upstream, where the water comes from, and the downstream, where the water flows to. Then defining in this way the left side of the bridge and the right side of the bridge. And finally, the center line, which is the imaginary line that goes along the initially taken survey and along which the bridge will be built. Our bridge, as said, are cable bridges, but in particular, they are wire rope cables, which is steel cable. They are steel cables made by a multitude of steel wires, as you can see in the section in the picture. Then I'm going to define the Crosby clips, which are devices composed by a saddle, a U-bolt, and 2 nuts, and they are made to clamp the wire cable to themselves, as you can see in the picture, and they're used like in the anchors of our bridges. And then we have a winch or cable puller, which is a manual pulling device used for operations like tower lifting or cable hoisting, as we're going to see. And now, as promised, let's see the main parameters taken into account for the design of our bridges. Firstly, the bridge needs to be built near the current crossing point for social reasons. If you build it far from it, then people could decide not to use it and keep crossing in the same old point and in the same old risky way, which you can see in the picture. And then free and safe areas for both abutments and footings need to be available along the chosen center line. Then the quality of soil, of course, needs to be assessed and approved on both expected positions of the footings. And once located possible position of the towers of the bridge, an adequate backstay distance needs to be surveyed in order to accommodate possible increase of design span in a second time. The height differential between the 2 sides of the center line needs to be kept in a limited range in order to have a design that is possible and efficient. And finally, like, we have the main question mark, which is like the history of the river, the hydrological history of the river, which we can explode in the following points. We can start with the status of primary and secondary banks, which is really indicative of the recent and past history of the river, giving us a first idea of how much setback is needed for the 2 footings. Then the upstream river shape will also be really important to be studied. An initial 50-meter span proposal, which could be this one in this case, could have to become 100-meter plus, just because the upstream meander, you can see here, could be expected to push little by little with erosion across the center line in the years. We're not talking about something that happens overnight. We're talking about something that could happen in years, and we need to foresee that. Also, upstream confluences need to be avoided as much as possible, as those are areas in which the riverbed could move across the entire valley during individual flooding events. And the high water level, it's probably the most important, let's say, technical information to be collected from the community people, I would say, in particular from the elders of the communities, because it will geometrically define the needed height of our walkway. Knowing the high water line, a freeboard value will then be defined to be respected by the design, and it goes between 2 and 3 meters generally for our designs. And as said, all of these considerations will be taken into account in order to decide where to place the footings with respect to the banks of the river. Let's now start diving a little bit more in the bridge design, looking to the main structural elements, starting from our foundations, which are made by footings and pedestals. The 2 concrete pedestals transmit the load coming from the top steel towers on top of the footing, which is below them. And the footing obviously spread it to the ground as a foundation. The suspension footing is a reinforced structure generally designed at 1 meter depth, so really shallow. It does involve a really simple excavation, and the rebar cage is then assembled inside of the excavation. And after a quick a quality check on dimensions, orientation, and rebar position and number, the concrete is mixed and poured. All concrete designs for B2P bridges consider a compressive strength of 10 megapascals. So basically like pizza dough, in order to account for the poor quality of the hand mixed concrete used on our site. And that gives you the idea of like the safety factors that we involve in our designs. Once the footing is casted and ready, pedestals are going to be built on top of it. Masonry or CMU perimeters are built around the assembled rebar cages, and eventually a first stage of concrete is poured using the same wall as a formwork, as you can see in the pictures. Once the first concrete stage is finished, then on top, we're gonna place the base of the towers and an extra reinforcing cage, and then pour a second and final concrete layer. One particularity of our suspension bridges is that the base of the steel towers is hinged. This means that the loads transmitted to these pedestals are going to be mainly of pure compression, and that the bearing pressure below the suspension bridge footings is checked and limited depending on the quality of the soil, of course, as every foundation. Flexural and shear capacity of the footings are also checked, and the pressure in particular is calculated using the equivalent width method, which some of you are probably familiar with here, if I'm not wrong. As said, the dominant check for the pedestals is compression verification, as long as the main, as the bottom of the towers is hinged and not able to transmit longitudinal moment, and then a transversal moment from the top of the tower will be transmitted in terms of a couple of forces, one of traction and one of compression in the two pedestals. And now let's talk about the towers, which are pretty interesting. They are laying on top of the foundation system that we just described. And the main elements of these towers, as you can see, are the two vertical steel pipes in red, with a T-base in blue that lays on top of the tower bases, which are embedded in the pedestals, as we saw earlier, creating in this way a hinged junction that we talked about. Finally, a bolted frame of angular braces in yellow is assembled on site and connects the two main pipes together, giving shape to the final entire structure. Here are some details of the main pipes. You can see the main pipe, vertical pipe with the base, the T-base that is gonna create the hinge, and then the lateral PL05. There are like plates that are gonna be connected with bolts to the X braces. Then on the left of this slide, you can see some details of the base that is embedded in the concrete, and you can see that it's topped up with a curved plate and closed with some bolts once the tower is in position. And on the right, you can see the top of the towers, which are made by a curved plate welded on top of the towers, which is gonna function as saddle for the main cables. And then there are gonna be two transversal plates closed with bolts in order to create a frame for the cables not to be able to jump out of their saddle. The suspension steel towers are assembled on the ground, and after placing the base of the main pipes in position on the pedestal, you can start connecting the X braces with bolts and then paint the tower. As you can see here, we're in Nicaragua, so it's blue, white, blue as the Nicaraguan flag. Then a temporary scaffold is erected in front of the pedestals and secured with lateral guide cables. And there will be a pulley system on top, supported by a timber frame. A lifting cable is passed through the pulleys, secured to the towers with slings, and eventually connected to. Are you guys able to hear me yet? Well, I just got the message that my connection is not good. Can someone confirm?
Yeah, we can still hear you, Nico.
Okay, good, fantastic. So I was going to say that the lifting cable is passed through the pulleys, secured to the towers with slings, and eventually connected to a cable puller, the winch that we talked about, to the other side of the scaffolding. A good anchor point needs then to be found or created in order to connect the other side of the winch. This will generally be a concrete block casted on site, as you can see in the sketch. The suspension steel tower lifting is one of the most dangerous steps for the construction of B2P suspension bridge. A lot of things could go wrong, and all the danger zones and the escape routes indicated in the sketch need to be delimited and evacuated. And good communication needs to be assured between the team that is pulling at the winch and the team that is checking the tower lifting at the tower position. And once everything is ready and the winch is set, then the hard work can start, and someone will start doing some good 15-20 minutes of rowing machine, little by little, lifting that heavy tower. And once it will start raising, it will be rotating around the hinge connection at the base, and it will hit the top timber structure, which will stop it with a precise cant, and the tower will then be secured with slings to the scaffold in order to be sure that it's not going to fall back. And finally, the bolts at the base of the tower will be secured as well. The inner part will be greased. Sorry, there is just someone with the microphone open. If it can be muted, it would be great. Fantastic, thank you so much. Structural analysis of each standard tower height have been run and parametrically studied in order to define optimal span ranges for them to work well both structurally and geometrically. So it's been already done at the beginning, and the calculations need to be rerun only if the specific tower that is used is going out of its optimal span range. And now let's pass to the peculiar anchor system of our suspension bridges that I mentioned. It's going to be an anchor beam, a dead man, we call it, underground with anchor blocks and transition arms. And as we're going to see, the main anchor beam in red is the main resistive body, and the transition arms in yellow transmit the load from the main cables to the anchor beam. And the anchor blocks in blue are the only part of the system out of the ground, with an embedded steel pipe as an anchor point for the main cables. The anchor beam is normally 3 to 4 meters deep in the ground, and that makes the excavation for suspension anchor generally massive. I say massive because we don't use excavators, we use hand excavations. As long as like our general sites are very rural and very remote and difficult to be accessed. This means that safety measures like grading with 1 meter steps, the excavation, shoring, or building protective barriers with handrail around the excavation are always applied in B2B sites. The anchor beam rebar cage is firstly assembled on the ground and then lowered at the bottom of the excavation with a rope system. Then the anchor arms cage are assembled and positioned, and finally also the anchor blocks once are assembled too. Then beam, arms, and anchor blocks are casted in 3 different stages in order to make it easier for the construction team to deal with the formwork. The most important reinforcing elements for this kind of anchor are the longitudinal bars, for sure, that are embedded in the transition arms, because those are the ones that transmit the load coming from the cable that anchors here the pipe on top to the beam at the bottom, which is the main resistive body. And then there will be the uplift check of the anchor beam that rely on the weight of the overburdened soil on top of the beam, summed to the weight of the beam itself, contrasting the vertical component of the force coming from the main cables. This check is carried out both in dry and saturated conditions. For the sliding verification, then, the beam needs to be able to resist to the horizontal driving force transmitted by the main cables. Active and passive soil pressure need to be considered, respectively, as driving and resisting forces. The main resistance comes from the friction at the bottom of the anchor beam, which is proportional to the sum of the vertical forces acting on the beam. And also this check is carried out both in dry and saturated conditions. And finally, we're getting close to the end, but we're still having a big part that is the walkway, the most interesting generally, that is made by these main elements list now. The main cables in yellow are anchored to the anchor blocks and pass on top of the top saddles of the towers. Then the cross beams in blue are generally composed by a steel section and a timber nailer connected on top of it with screws. The suspenders in red are made by 10 millimeters rebars, which are connecting the cross beams to the main cables. Then the restraint cables in green keep the suspenders distanced from each other and also partially function as a handrail cable, as you can see. The longitudinal timber boards are connected with screws on top of the nailers that are topping the cross beams. And finally, the fence is normally made by mesh fencing, as you can see in the picture. The main cables will need to be transported by hand from one side of the river to the other. I was not kidding when I was talking about hand excavation. We do everything basically by hand. And workers will have to climb on the scaffold towers in front of pedestals in order to lay the main cables on the towers top saddles. When we talk about climbing scaffold or working in height, we're always talking about using harnesses and lanyards or self-retractable devices. So we're always complying with OSHA standards during our construction works. The cables then pass behind the towers and then will go and anchor to the anchor blocks. Once they are anchored, they will be clamped with Crosby clips that we described before, as you can see just in red in the sketch. And finally, they will be hoisted. The cable will be hoisted using a winch until reaching the hoisting sag, which will be the height of the cables defined in the design. This procedure, as the tower lifting, is very dangerous, and the danger zones, escape roads, needs to be defined and marked as in the other procedure. You can also have a glance to the connecting loop that is used to pull the main cables using the winch that I described earlier, anchoring the winch to the anchor block. Meanwhile, while we are pulling the cables, which takes generally like 1 to 2 days, the suspenders are cut and bent following the measurements given by the suspender schedule, which comes with the construction settings. Because this type of bridge, every suspender is different from the other, as you may imagine. While in the suspended bridge, which is a hammock type, the walkway and the cables have the same shape. In here, they have a different shape, so that's why. The suspenders are then assembled, and the crossbeam are laid near the tower in order to be lifted and launched. And a group of workers will be set on top of the front of the scaffold of the tower and waiting for a second group of workers to lift the suspenders in front of them with a system of ropes. Each suspender will be looped from the top team around the main cables and connected to the marks on the restrained cables with clips, as you can see here. And then like the main loop will be closed with another clip. When we have a suspender that needs to be too long and they need to be overlapped, we have this kind of connection in between the two suspenders. Finally, on both sides, we will have launched the suspenders, and we will see for the first time the profile of the walkway getting in shape. And that's the time in which we want to start gathering longitudinal timber boards near both towers in order for having two construction teams from both sides starting connecting dots, basically. And here we are with front team connecting the boards, and a third person generally feeding them boards and material. This happens on both sides simultaneously. You can see that for this kind of working at height, we need a a safety line on top on which to connect self-retractable lines. The safety line is basically as the same kind of main cable with steel wires that pass on top of the top brace of the main towers with a padding in between, just like to make sure the friction doesn't ruin the cable or the tower. And at mid-span, the cables will be low enough for workers to be connecting directly to them and not to the safety line if they want. Once the two construction groups will meet at the mid-span, then the walkway surface is finalized, and it's time to install the fence, which is going to be assembled to the lateral timber curb on the ground and then transported on site, on the walkway, and connect the lateral curb will be screwed into the top timber of the walkway, obtaining a detail that looks like this or like this. The last step is to cast an approach slab to level the ramp with the walkway and to avoid tripping hazards. And here are the same detail from above. And this walkway system is designed to withstand the AASHTO distributed live load described here, which goes from around, let's say, 3 kilonewton to around 4 kilonewton, depending on the total walkway area. Every single structural element will also need to be able to withstand a local concentrated load of 2.22 kilonewton, so always coming from AASHTO, and the wind load related to a wind speed of 160 kilometers per hour, which is more or less 100 miles per hour, is considered acting on the entire structure, which is pretty high. The analysis behind the cable design starts with the determination of the horizontal component, pH, which is a constant along the bridge. from which then every needed component can be calculated simply using trigonometry. The safety factor considered for the main cables is 3.0. And the minimum safety factor, let's say that. The backstay forces rely on horizontal equilibrium of the top of the tower, and is because the tower is able to rotate. And the goal sag level for live loads is normally the span divided by 11. And here are some examples of what a suspension bridge look like on inauguration day, but also on a normal day. It always looks good, generally. It's just like such a beautiful type of structure. And it's really scenic in these kind of valleys. And finally, new developments. Let's talk about steel decking. Timber decking has always been a challenging element of our bridges, easily sourced by local communities, but with a really short life cycle, 4 to 7 years if we're lucky. Increasing in that way the maintenance costs over the years. For this reason, we have been piloting a new grating deck design in our Rwanda program throughout 2020. The system is composed by hot dip galvanized grating panels with bottom plates to be fixed with bolts to the steel crossbeams. Lateral concrete curbs are then fixed with bent rebars to the grating panels in order to guarantee adequate mass to the system, which would be too light if not. These grating panels are sourced outside of Rwanda, as long as in Rwanda there's still no possibility of a hot dip galvanization, which was the solution that we went for, and not existing a real market for it. Another remark is about COVID and safety on site. We have always operated with safety first mentality, providing full PPE protections to all of our workers. But as you all know, COVID brought this topic to a whole different level. But COVID found us prepared. We quickly updated our safety protocols with COVID preventive measures in line with the national Rwanda requirements. In this case, we're talking about Rwanda, like social distancing of 1 meter, providing face masks, checking the temperature, and providing hand washing stations to all workers. And we have been able to keep building our bridges throughout this pandemic, assuring the safety of our workers and of the same people of the remote communities that we work to serve. Finally, it is important to mention again that throughout the last decade and more, we have been partnering with a lot of the best firms in the engineering and construction world, which you find represented in the slide. And it is worth highlighting that a meaningful portion of the revenue each year for B2P is earned through the corporate partnership. And if you have any question for that, if you or your company are interested to collaborate, you will contact Devin Connell. Thank you so much for your time. Sorry if I got a little long. We still have some minutes for the Q&A, and here are our contacts. Thank you so much.
Thank you, Nico. Thank you, Devin. Just to getting back to the question and answer session. So there are lots of questions here, and I'm going to be selecting a few and keeping the time restraint. The first question probably is interesting. Do you have any suggestions for internship volunteer work for engineering student? Someone is looking for a volunteership internship. Who should they contact you? Devin.
Yeah, great question. If you're interested in volunteering, definitely reach out to me, send me an email, and I can give you some more information. With the current kind of climate and our kind of restrictions and operations from the past year, we actually don't have a lot available at the moment, but that fluctuates on a timely basis. We also partner with an organization that works with university groups specifically. It used to be part of our organization, and then it kind of separated out to focus specifically on university groups. So much like EWB university groups, they have bridge chapter university groups, and I can introduce you to them as well. So yeah, I'd say if you're a university student and interested in getting involved in this type of work, feel free to send me an email.
Thank you, Devin. Second question, who is taking the structural responsibility for the design? How much does the bridge cost per 100-foot span? Cost of the bridge, I guess.
Nico, you want to take the design and I'll cover the cost?
I can take I can take the design. So what we generally do in Rwanda specifically is that we take ownership of design and technical problems for the first year of the bridge. And in between the first handover, and then there will be an official handover in which the full responsibility of maintenance and everything will go to the district after that day. But the design is all made by B2P and approved by the district.
Yeah, and just to add on that a little bit, I know there's another question in here about maintenance. We do train our communities in maintenance and work with the local districts on maintenance and inspection as well. So we have our own maintenance and inspection program, but just like any other infrastructure, the local governments own the projects after they're complete. So like Nico said, after a year, any typical maintenance is on them. However, we'll do inspections, we'll provide them reports, we'll work with them to make sure they're able to provide necessary work on the projects over the next several decades. And the cost of bridges, they vary depending on a lot of different factors. Anchor sizes, obviously, ramp sizes, span length, but it's not just span length, so it's hard to break it down by per meter per bridge. But they really vary anywhere. We used to say 60 to 100. Realistically, now it's a little bit more. It's more like $80,000 to $120,000 in total cost. So that's all operational costs broken down between all of our bridges that we build. Materials alone specifically are closer in $30,000, $40,000, $50,000 range. But it depends on what we're getting donated. Sometimes we get steel pipe. Sometimes we usually get cable donated. But all of those factors can adjust those costs.
Thank you.
It's also worth saying that the district is paying for local materials like concrete, like cement, sand, gravel, and local labor, and rock as well. So it's a collaboration in between B2P and the districts.
Nicola, when you say district, is it the local jurisdiction you're talking about, or the?
Yes, this is the district is the local jurisdiction, but we in Rwanda in particular, we signed an MOU with the central government, which coordinates the works with each district, basically.
Another question from regarding how does this compare with the New Zealand design construction suspension bridges in Nepal? Have you guys seen that, or any comment on that?
Yes, so a lot of our design has been inspired by all the bridges built in Nepal, which a lot of them are related to another big organization that is called Helvetas, and the main design ideas come from them, and then we just shape them, and we keep shaping them little by little through the years, but they definitely set a big example for us to follow.
Okay, probably you may have answered these questions. What code do you follow in the design? AASHTO?
Yeah, so we generally as B2P follow AASHTO, but in Rwanda, for example, the main code, the reference code is the British standards. So basically similar to Eurocodes, meaning we're always up above with our safety factors that are very, we are basically above all codes. We're trying to be very safe, considering the places where we build.
Okay. Another question is on, I saw some questions on corrosion. Any comment on that? How do you take care of corrosion issue? What standards do you use?
Yeah, for the corrosion, for the main cables, the 3+ safety factor provides a protective layer of corrosion to the cables that that will accompany them, like bring them throughout their life with no problem. For the towers, we use protective paint, and we also account for some millimeters of corrosion. So even the thickness of the tower accounts for a protective layer of corrosion creating. And so yeah, those are the ways, basically staying very, very on the safe side with thicknesses.
Okay. Another question, have you ever considered using a fabric rope instead of steel? My understanding that it lasts longer since it does not corrode and may be cheaper.
Yeah, I mean, it could be used. It would change the design. It would change it also, like in terms of procurement, could be different, and the cost could be different. It could be definitely taken into account for a possibility, but it's not right now. We are continuing with standard designs that work and permit us to have a system that is able to speed out a lot of bridges every year, which is working.
Okay, last question. Do you guys involve, do the native people, local residents are involved in construction? Are you involve them during this bridge construction? That's the question.
Sure. Every time that we work on a bridge site, we generally send a foreman, which will be on site throughout the entire construction of the bridge, which generally lasts like 3 months. 2 to 3 months, and during that time, the project engineer will be every now and then just like supervising the site, and the foreman will be in charge of enrolling up to 25 local labor, which come from the same communities that are served from the bridge. So the same communities are gonna also get a possibility of being employed for shifts that goes, I think, every 2 weeks. We change our laborers in order to give more enrollment, if that makes sense.
Okay. Thank you, Nico, and thank you, Devin, for the wonderful presentation. Particularly Nico, it may be way past your time over there, and thanks for accommodating us. Much appreciated. And thank you, everyone, for attending this. If you have any further questions, you can shoot an email to Nico or Devin. Their email, you can see their email on the screen. And thanks again on behalf of SEONC for attending this presentation. Thanks.
Thank you so much, everyone. Please really feel free to reach out to me and Devin. We'll be happy to answer to all your questions. Thanks again, and enjoy your day.
Thank you.